To safely store sensitive information in the cloud, you have to lock it inside a cryptographic vault. That is the baseline rule of outsourcing data. But traditional searchable encryption algorithms are highly rigid. They demand absolute mathematical perfection from the user. Humans type fast, and we make mistakes constantly. We hit the D instead of the K and type netword, or swap our fingers and type secure instead of secure. You can't just run a standard spell check to fix this. The cloud server is mathematically blind. It can't read your search query, and it can't read the encrypted files it holds. Because of that blindness, a single misplaced keystroke completely alters the underlying search request. The server sees 0 matching files, and the search fails entirely. Engineers had to design the method that allowed a blind server to forgive human error without ever compromising the encryption itself. The earliest fix was the wildcard method, brute forcing a massive dictionary of every possible one-letter typo. But generating these variations creates an exponential data explosion that chokes server storage. Worse, with 2 typos, the method collapses. Solving this required a highly specific mathematical tool, Locality-Sensitive Hashing, or LSH. Standard cryptographic hashes operate on a strict rule. If you change a single letter in an input, the resulting output is completely scrambled and randomized to protect the data. LSH does the exact opposite. It maps similar inputs into the exact same output bucket. By treating words as mathematical vectors, LSH measures the Euclidean distance. If a typo lands close enough, the 1s and 0s align, confirming a match. The system can finally find your file because it is searching for mathematical proximity, rather than demanding an identical string of text. Let's look at one of the most common human typing errors, swapping 2 consecutive letters, hitting the R before the U in secure. Early LSH models broke down search terms using bigrams, which chop a word into overlapping 2-letter chunks. If you swap one letter, it shatters multiple bigram pairs at once. The Euclidean distance between the correct word and your typo spikes, pushing it too far away to register as a match. To solve the swapped letter problem, researchers stripped the mapping process down to its most atomic level using unigrams. Instead of tracking sequence, a unigram model ignores order entirely. It tallies how many times each letter appears. When you type secure, the underlying count is identical to the correct spelling. The Euclidean distance barely registers a difference, keeping the search safely on track. By deconstructing words into raw letter counts, the search algorithm completely neutralizes the chaotic mechanics of human error. Applying this unigram mapping to LSH algorithms yielded highly accurate results for multi-keyword searches in the cloud. This chart compares exact match precision to fuzzy match precision. Even with missing letters or swapped keys spread across multiple words, the system accurately retrieves the correct encrypted file up to 90% of the time. You get the cryptographic strength of a steel vault, paired with an interface that easily forgives a messy keyboard. Organizations no longer have to choose between locking data away from external threats and keeping it easily searchable for their own workforce. A reliable search system accounts for the physical reality of human typing. It takes our flawed inputs and correctly interprets the intent behind them.